All right, according to the poll, you like this kind of lecture the best. This is what won out, so I'm going to do this. Okay, section 1.8, exponential and logarithmic functions. All right, so you've been looking at E all these years, and you've been told, okay, well, E is the natural number about 2.71 and so forth, okay? But in calculus, a lot of time we define E as the limit as x approaches infinity of 1 plus 1 over x to the x, or the limit as x approaches negative infinity of 1 plus 1 over x to the x. All right, later on throughout the semester, as we learn more, we're going to go back to this part, okay, how we get E out of that. All right, for now, let's focus on this kind of stuff, okay? Remember, if you have log of x, doesn't it mean log base 10 of x? And if you had ln of x, or natural log of x, that's the same thing as the log base e of x with the natural number. Keep that in mind. All right, here we have some properties of logarithms. It says log base b of b to the x is equal to x. So what does that mean? That means if your base here is the same as the base in your argument, you just drop all of that stuff and you just let it equal to the exponent. Here, if you have b raised to the log base b of x, where this b right here is the same number as that b right there, you drop everything except that argument or logarithm, and that's for x is greater than or equal to 0. Okay, and these you can read through, but really, I got to memorize this one and this one, because all this really is a special case of these two. So if you have these two memorized, you automatically have those two memorized. Because remember, what is this? This is really just what? Log base e of e to the x is equal to e, right? I call this log base e instead of natural log. Now, if this is really the same thing as that, it's really exactly the same property that we have right here. What I write wrong here? That needs to be what? X. And it's exactly the same property that we have up here. Just the b happens to be e in each case. Basically the same thing right here, okay? That's really what e to the log base e of x is equal to x. In that case, it's really the same thing as this, is just the b's happen to be e's. Okay, let's look at our theorem that we have next in the notes. Let's look at that theorem that we have next. Okay, so we have a theorem that says this. If b is greater than 0, if b is greater than 0, b is not equal to 1 as well. A is greater than 0. C is also greater than 0. And R is any real number. And R is any real number. Then we have this, part A. Part A says, what if we have the log base b of a times c? We could do a rewrite and call that the log base b of a plus the log base b of c. All right, part B. Part B says, what if we have the log base b of a over c? Then I could do a rewrite and call that the log base b of my numerator minus the log base b of my denominator. All right, then we have part C. Part C says, what if we have the log base b of a to the r? We could rewrite that as r times the log base b of a if we needed to, okay? That last property, don't worry about that one, part D, because if we know these other properties, we could actually figure out that last one according to just memorizing these. So there's no point memorizing extra if you don't need to. All right, so keep these in mind. Keep in mind those properties we had a little while ago. And we're going to work with them. I don't have enough board space right here to keep everything on the board. So let's move on to our example. Find the exact value. Find the exact value the exact value without using a calculator. I'm just going to shorten it here. Part A, we have log base 3 of 81. All right, let's think about those properties we had a little while ago. What was that? Something like log base b b to the x is equal to x, right? What else do we have? B raised to the log base b of x was also equal to x. All right, I'm going to do a rewrite. I'm going to call this log base 3 of, now 81 is just a power of 3, right? Let's see, 3 times 3 is 9, times 3 is 27, times 3 is what? 81, so that's the what? 3 to the 4th. What does this property right here tell me? Tells me if this base is the same as the base in the argument, in other words, is this 3 the same as the 3 in the argument? Sure is, so I can drop everything except what? The exponent here. Part B. What about the log base 2 of 1/8? Well, let's see. I'm going to try to get this 2 to match a 2 in here, kind of like this part right here. Well, first of all, I'm going to say, okay, well, this is the same thing as log base 2 of 8 to the negative 1 is my exponent, right? So how about this? How about if I say this is log base 2 of, let me put a negative 1 on the outside like that. And 8, I could say is what? 2 cubed like that, right? Do y'all agree? That gives you the same thing. 2 cubed is 8, and it's raised to the negative 1. So this is the log base 2 of, what do you do with an exponent to an exponent? You multiply the 2. 3 times negative 1 is negative 3. Now, does this base match that base there? And like this property right here? Yes, everything drops out except the exponent, which is negative 3. C is in cat. We have 7 raised to the log base 7 of 3. Looks a lot like this property right here. 7 to the log base 7 of 3. So I drop everything except the what? Except the 3. So there's no work to do really on this one. But D. D is in dog. Natural log of e to the 5th. Natural log of e to the 5th. Well, what is that? That's just this property, right? I have an understood e right here. I have an e right there, so I drop everything except the 5. Well, that one was easy enough, huh? Too bad it can't be all that easy. All right, next example. Rewrite as a single logarithm. Rewrite as a single, I'm just going to abbreviate here, single log. Part A. Or, no, we don't have part A. We just have one part. 1/2 times the log of x minus 3 times the log of sine of 2x plus 2. How dare you put a sign in the logarithm? Well, it'll be all right. All right, so I want to write that as a single logarithm. Let me see. Let me use those properties I had earlier up here on the board. What do we have? We had something like the log base b of a times c was equal to the log base b of a plus the log base b of c, right? So we said if we have a log of two things being multiplied in the argument, I can add logs of those two things, right? But think about equality. If the left is equal to the right's equal to the left as well. I'm going to use that, or maybe use it later on, okay? Same thing with this. We had, try to write that a little better. We had a log base b of a over c was equal to the log base b of a minus the log base b of c. And then we had what, like the log base b of a to the r, I think they used, is equal to r times the log base b of a. All right. Keep in mind, the left side is equal to the right side is equal to the left. So what is this saying? If I have some number r multiplied by the front of my logarithm, I could take that number r and I could bring it to the exponent of the argument like that. Isn't it the case right here? I'm gonna have some number here multiplied by that logarithm. So I could take that number and bring it to the exponent of the log. So I could do a rewrite here. I could say that's a log of x to the 1/2 like that. What about this 3? Can I do the same thing with this 3? It's multiplied by that logarithm, so I can bring it to the what? Exponent of my argument. So I'm going to say minus the log of the sine of 2x cubed. Now I'm going to put a bracket to denote all that's argument plus 2. All right, so for right now, I'm just going to bring this down to log of x to the 1/2 minus the log of, now remember, a simpler, a neater way to write this is sine of 2x cubed like that, plus 2. Now for Wiley, you're going to have to keep it that way, okay? But this is fine for, like if you're taking a paper and pen test or whatever. All right, I'm trying to write this as a single logarithm. I have two logarithms here, right? So I need to combine those. What does this say right here? If I'm subtracting two logs with the same exact base right here, look right here. I'm subtracting two logs with the same exact base. It's understood to be 10, right? Then what can I do? I can rewrite that as the log of the first argument over the second argument. So I'm going to do a rewrite here. I'm going to write that as one log of the first argument next to the 1/2 over the second argument, sine of 2x cubed plus that 2 over there. Let me see if I could take these two and write them as one logarithm as well. How about 2? Let me see if I can get fancy with that 2. What if I were to ask you this? What is the log base 10 of 10 squared? According to this property right here. I'm sorry, this property. I have a 10 there, a 10 there. I could drop everything except what? The exponent of 2, right? So yeah, this stuff is equal to 2, but is it 2 also equal to this stuff then? So instead of 2 right here, I could rewrite that as a log base 10 of 10 squared. I'm going to do so. So this part just comes down. But we just said instead of 2, I could write that as log base 10 of 10 squared. Write that a little better. Now I have two logarithms of the same base being added. What does this tell me right here? Two logarithms being added with the same base. I can multiply their arguments. So I'm going to multiply 10 squared by this part. So I'm going to have the log of 10 squared times x to the 1/2 over the sine of 2x cubed. All right, maybe I'll do a rewrite up here and I'll say, okay, that's a log 10 squared is just 100. X to the 1/2 can be written as the square root of X. It's fine if you leave it to X to the 1/2, but I'm going to simplify, or I like this way better. It's not really simplifying. And then I'm going to write the sine of 2x cubed. There's my single logarithm. All right, let's look at what's next here. Solve without using a calculator. Solve without using a calculator. Solve without using a calculator. Part A. Part A, we're going to have log base 10 of square root of X is equal to -1. A lot of this section, you're probably thinking, why is it in calculus? You know, this was pre-calculus stuff. Well, we're going to use it later on as why. We're going to use these properties later on whenever we get into derivatives, and it'll help us out. All right, so if I want to solve this without using a calculator, I'm going to convert this to an exponential. Remember how to do that? You take this base raised to the other side, so 10 to the -1 is equal to the argument, square root of X. Well, what's 10 to the -1? 1/10. And how do you undo that square root? Square both sides. So 1/10 squared is equal to the square root of X squared. Square your top, square your bottom, you get 1/100 is equal to X, right? Now, whenever you're dealing with solving where you have an X in the argument of logarithm, check to make sure this is okay. Can I put 1/100 in here? Yes, I sure can. What would I not be allowed to put in the argument right here? Something that is not positive, or something that comes out to, say, a negative or a 0. If I substitute this in, it will not come out to a negative number. It will not come out to a 0. So this is indeed my answer. B. How about natural log of 1/x plus natural log of 3x cubed is equal to the natural log of 10. Let's see, how are we going to solve this? First of all, I'm going to use my properties of logarithms. I have two logs with the same base being added. So what do? I multiply the arguments and write it as one log. So I'm going to say that's the natural log of 1/x times 3x cubed. Notice I'm multiplying the argument. It's equal to the natural log of 10. So this will be the natural log of 3x squared, or take it what? Let me just write it this way. 3x cubed over x is equal to the natural log of 10. What happens here? We get natural log of 3x squared is equal to the natural log of 10. Now, what happens if you have natural log is equal to natural log without no plus or minus or anything here or there? Then you could drop these natural logs and just set the arguments equal to each other. So 3x squared is equal to 10. Now we know how to solve this. This is what? X squared is equal to 10/3. Take the square root of both sides. And we get x is equal to plus or minus the square root of 10/3, right? Now, remember, whatever's in my argument has to be positive. Can't be 0, cannot be negative. So what happens if I put negative square root of 10/3 in here? I'll get 1/negative, which is not allowed. So I got to throw away the negative. So I could say the positive of square root of 10 over 3. Now, if I plug in the square root of 10 over 3 here and here, it's going to be positive in each argument. How about C? Same directions here. C, we're going to have 8 to the x is equal to 15. Now, you may do this one a little differently to me. There's more than one way to solve this one. I don't know. I see 2 different ways right away. I'm just going to choose one. One way is you could take the natural log of both sides. So I'm going to say the natural log of 8 to the x is equal to the natural log of 15. Use that property of logarithms. It says take this exponential argument, bring it to the front. So x times the natural log of 8 is equal to the natural log of 15. And then divide both sides by the natural log of 8. X is equal to the natural log of 15 over the natural log of 8. That's one way to solve it. But D is in dog. D is in dog. D is in dog, we're going to have e to the 2x minus 2x e to the 2x is equal to 0. Let me see, how am I going to solve this? What could I do here? Well, if I try to solve for x straight, kind of tough, right? But can I factor an e to the 2x out of both of these terms right here? So let's take e to the 2x out. If I take it out right here, I'm left with 1, minus if I take it out here, I'm left with 2x. Now, what do? We take each one of these factors here and set them equal to 0. So e to the 2x is equal to 0, and this part's going to be equal to 0. E to the 2x is equal to 0. Make that look better. Well, let's see. E to the 2x is equal to 0, and 1 minus 2x is equal to 0. This part's easy to solve. Negative 2x is equal to negative 1, so x is 1/2, right? How about this part? How can I solve it? Could try a few different things. One thing I could try is, what could I let x be to make this a true statement? You might be thinking 0. But let x be 0. 2 times 0 is 0. E to the 0 is 1. So 1 is not equal to 0. That doesn't work. What if I try a 1 there? Well, e to the square certainly is, or e squared is certainly not 0. What if I choose negative 1? E to the negative 2 is 1 over e squared. That's not 0. This part actually gives you no solution. But this whole equation right here does have a solution, which is this. So just box in that part. All right, and finally we come to our last example for this section. This short section, so part of the class period today is going to be this section. The other part is going to be the first part of section 2.1. Suppose I have the limit as x approaches infinity of e to the 8x plus e to the negative 8x over e to the 8x minus e to the negative 8x. All right, let's see. What in the world do I do right here to evaluate this limit? If I try to evaluate this, I get infinity right there. I get 0 here. Get infinity there, minus 0. So I get infinity over infinity. Indeterminate there. So I need to come up with something else. How about I try to factor? Like up top, what if I try to factor e to the 8x out the top? Well, what am I left with here? E to the 8x times what gives me e to the 8x? Yeah, 1. This is the tricky part. How about this? Will that give it to me? Well, let me ask you this. What if you distribute in this e to the 8x? Will you get that out? What's e to the 8x plus e to the negative 16x? Let me go off to the side. Do some scratch work. E to the 8x times e to the negative 16x. What do you do if you multiply two things with the same base? Like let's say you had x squared times x cubed. What do? You write the base down once and you add the exponents. You say 2 plus 3 gives me x to the 5th, right? Same thing here. Keep the base the same and add your exponents. What's 8x plus negative 16x? Negative 8x, which is what I wanted, right? That works. Factor e to the 8x at the bottom. What are you left with? 1 minus what? E to the negative 16x again. Oh, do you see what I see right here? These two divide out. Life's good. So we have the limit as x approaches infinity of 1 plus e to the negative 16x over 1 minus e to the negative 16x. And you don't have to do this part, but I'm going to do a rewrite. I'm going to say that's the limit as x approaches infinity of 1 plus 1 over e to the 16x over 1 minus 1 over e to the 16x. In other words, making those exponents positive. Now let's try to evaluate this. See if I get an indeterminate form again. Limit as x approaches infinity of 1 is just 1. How about the limit as x approaches infinity of this? That'll give me 0 over 1 minus 0. Well, what's 1 over 1? 1. So that's all there is in section 1.8. We're going to start 2.1 today as well. We're not going to finish 2.1 today, so we'll start it today, continue it Tuesday.